Welcome back, everyone, to another explainer. Look, if you've ever practically banged your head against your keyboard trying to securely connect to a remote server, or you're just sick of clunky VPNs slowing your workflow to a crawl, you are exactly where you need to be. Today, we're diving into some serious networking magic called TLanX. Think about our modern setup for a second. Our devices are literally everywhere, right? You've got a laptop at home, a server floating in the cloud, maybe your phone bouncing around on a cellular network. Well, TLanX acts like this invisible glue. It magically snaps all those scattered devices onto a single, private, fully encrypted virtual LAN. It literally doesn't matter where they physically sit on the globe. They get stable, private IP addresses that never change, even if you're hopping between networks. It's a total game changer.
Okay, let's dive into this. We've got this broken down into logical, bite-sized chunks so we can cover the whole shebang easily. First, we'll meet the mesh VPN. Then we'll look at the control versus data plane, unpack the core network concepts explained, get into shaping and securing traffic, check out deploying TLanX in action, and finally figure out exactly when to use TLanX.
Section 1. Meet the mesh VPN, decentralizing your network.
Let's zoom out and look at the macro perspective first. Just imagine the physical reality of how we work today. You want your home laptop, your cloud server, and your phone on mobile data to all talk directly to each other, exactly as if they were plugged into the same physical switch in the same room. That is the decentralized reality a mesh VPN actually creates. Think about the traditional hub-and-spoke VPN for a second. We've all used these. Every single packet of your data gets funneled through one central server. It creates a massive central bottleneck. And honestly, it's kind of wild to think that traditionally, a single machine just sits in the middle, funneling and potentially snooping on all your traffic. Now contrast that with the TLanX. TLanX builds direct, peer-to-peer tunnels between your devices whenever the network allows it. This means your traffic takes the shortest possible path, zero central bottleneck, and absolutely no single machine sitting in the middle hoarding your data. It is a completely decentralized approach.
Moving on to Section 2. Control versus data plane, separating the brains and the brawn.
Now, what's really interesting about this architecture is how it answers a very logical question. How does TLanX actually manage to scale so efficiently without that central bottleneck? Well, it pulls it off by splitting the workload into two completely separate planes. Take the control plane, for example. This is the TLanX server, and you can really think of it as the brains of the operation. It holds the absolute source of truth: who owns which networks, which devices are enrolled, what IP addresses they get, and the access rules. It handles all that lightweight coordination and authenticates your agents. But here is the absolutely crucial part. The server never, ever carries your actual application traffic. That heavy lifting belongs to the data plane. This is the brawn. These are the encrypted tunnels formed directly between your agents. Once the control plane introduces two devices, they spin up a direct tunnel, and your actual traffic, whether that's a quick ping, some SSH terminal commands, or heavy web traffic, flows straight between them. It perfectly separates the lightweight server coordination from the heavy lifting of moving your end-to-end encrypted bytes.
All right, Section 3, Core Network Concepts Explained, the building blocks of the mesh.
So now that we have our heads around the macro architecture, let's zoom in a bit and decipher some of this networking alphabet soup. We're going to start with the primary actors. First up is the agent. This is a lightweight program running quietly in the background on your device. Its job? It authenticates to the server, spins up the virtual network interface, and manages the actual tunnels. The beauty of this is you don't need clunky hardware firewalls or specialized routers. The agent is essentially the device itself as it appears in your dashboard. And it's wildly flexible. A single agent can join multiple networks simultaneously. You can run it in full mesh mode, where everyone talks to everyone, or lock it down in isolation mode, where agents only connect through designated hubs. Next on the list, we have a peer. You can think of a peer kind of like a coworker in the same virtual office. If your laptop and a server are sitting in the same TLanX network, they view each other as peers. Simple as that. When you pull up the TLanX dashboard, you actually get to see this live matrix showing exactly who is connected to whom as peers. It's basically just the perspective of one device looking out at the rest of its trusted network. Then, of course, we have the network itself. In the TLanX universe, a network is a logical grouping of these agents that all share one single private IP range. You know, like a CIDR block, something like 10.0.0.0/24. By default, agents in different networks are completely isolated from each other, but you can run multiple independent networks side by side without them ever crossing streams. Oh, and behind the scenes, TLanX servers run as clusters of nodes. This ensures high availability and makes sure your agents are always served by a node that's geographically close to them to keep things super fast. But hold on. Here's a question that always comes up, and it's a good one.
What happens when your devices are trapped behind a completely locked-down, hard firewall? We just hyped up these direct peer-to-peer tunnels, but what if advanced NAT Traversal, basically the magic trying to punch a hole through the router, just straight up fails to get a direct connection? Does the whole mesh just break?
Thankfully, no way. It survives. This brings us to the brilliant concept of relays and peer relays. When two peers genuinely cannot reach each other directly, TLanX elegantly falls back to a relay machine that simply forwards the packets between them. And here is the genius part. Any agent in your network with a public IP, like a random cloud server you have running, can act as a peer relay. This means even if you're stuck in a hotel with literally the world's most restrictive Wi-Fi, your mesh won't break. It just takes a slightly longer but equally secure path. So if you ever see a relay connection status in your dashboard, don't panic. A relay rescue is totally normal for hard NAT devices, and your data stays 100% end-to-end encrypted.
Okay, moving right along to Section 4, Shaping and Securing Traffic, Rules of the Virtual Road.
Let's transition into the microscopic rules of how data is actually shaped once that mesh is established. The virtual network interfaces created by TLanX come in two main flavors, Tune and Tap. Tune operates at layer 3, carrying IP packets. This works seamlessly on every platform, and frankly, it's the right default for almost all use cases. Tap, on the other hand, operates down at layer 2, carrying raw Ethernet frames. Why would you need that? Well, it supports non-IP protocols and network broadcasts, making it fantastic for legacy applications or device discovery on a local network. Just keep in mind, you pick this mode per network when you create it. Oh, and a quick aside, macOS will always fall back to Tune anyway because it actually lacks a native tap driver.
So the crucial point here is how we control who sees what on these interfaces, and that's handled by access control lists, or ACLs. By default, once you're in the mesh, every agent can reach every other agent. But the very second you flip an ACL on, the entire network transforms into a firewall. The default posture immediately snaps to deny. This is the core of modern zero-trust security. Nobody gets in unless they are explicitly allowed. From there, you can create super granular rules based on connections between agents, specific subnets, or exact ports and protocols. And the absolute best part, these ACLs enforce real-time security across every single agent in the mesh within seconds. You change a rule in the dashboard, and bam, it's applied globally.
Which brings us to Section 5, Deploying TLanX in action from zero to mesh. Let's move to the practical side and see how this builds out in a real-world deployment. How hard is this to actually set up? It's incredibly elegant, literally just a 5-step process. First, you run or log in to a managed TLanX server cluster, which is your control plane. Second, you install the agent on your devices and enroll them using a simple zero-config registration key. Third, you create a network and let the server assign each agent a virtual IP from your chosen block. Fourth, the magic kicks in. Agents instantly discover their peers through the server and build those direct tunnels automatically. They only use relays if firewalls force them to. Finally, step 5, you manage your security centrally via the dashboard by setting up those ACLs and subnets. Notice how brilliant this is? Everything after step 2 is configured centrally and pushed out automatically. You are managing a global mesh from one single pane of glass.
And finally, Section 6, When to use TLanX, Real-World Applications.
Now to reward you for sticking through all those technical mechanics, let's talk about the massive utility here. This brilliantly illustrates how all that theory turns into a real-world game changer. Think about these applications. You can access services behind a strict NAT router without ever opening dangerous ports to the public internet. You can provide your remote team with private, encrypted access to internal servers. You can seamlessly bridge entire subnets site to site, meaning a laptop sitting in a coffee shop can seamlessly print to the office printer or check a remote security camera. You can enforce strict least privilege access using those per-agent firewall rules we just talked about, and you can maintain high availability through automatic failover gateways. TLanX completely solves the headache of distributed environments by giving you one flat, perfectly secure address space no matter where the hardware actually lives.
Look, if all your devices literally never leave the same physical room, you probably don't need a mesh VPN. But the very second they spread across different locations or networks, the old rules simply don't apply anymore. Which leaves us with this final thought. If geography no longer dictates your network boundaries, what will you build? It completely challenges our traditional physical networking mindsets, doesn't it? Thank you so much for joining me for this explainer. Keep learning, keep building, and I will see you in the next one.